Right. So we're going to take a look at wave motion. Right. So again, I'm telling most of the things that you should know already, right? Right. Wave motion is a means of transfer of energy from one point to another without there being any transfer of matter between the 2 points. Waves can be classified as being mechanical, or waves can be classified as being electromagnetic, right? Mechanical waves are produced by a disturbance in a material medium and are transmitted by the particles of a medium oscillating to and fro about the equilibrium position, right? Mechanical waves, therefore, require a material medium for the propagation. Here are some examples: water waves, waves on a spring, sound waves, and waves in a string. All right. Electromagnetic waves, on the other hand, consist of a disturbance in the form of varying magnetic and electric fields. No medium is necessary. However, EM waves travel more easily through a vacuum than through matter. Here are some examples. You should recognize some of them, right? Right. We have to know a few other wave classifications. Right. A non-periodic wave or pulse consists of a single wave front and is produced by a single disturbance. A periodic wave is produced by succession of periodic disturbances, which give rise to a wave train, right? So you have a pulse, and then when you have these successive pulses, right, moving in a particular direction, you end up with your wave train. All right, that's one way to look at it, right? Energy motion, energy movement. A progressive wave is one in which there is a transfer of energy from the source to the space, to the places around it. And then this new one here that we're going to focus on is a stationary wave. A stationary wave is one in which there is no net transfer of energy. However, there is an interchange of energy, right? So there's a constant interchange of, like how you have kinetic to potential, right? But there is no net transfer of energy from one point to the next. So basically, energy is just being interchanged, right? High, low, and so on, right? Direction of displacement. A transverse wave is one in which the oscillations are perpendicular to the direction of the wave. For example, a water wave waves in strings, and EM waves and waves in a spring. Then you also have longitudinal waves. So by the way, right, if you use the slinky, you might remember this. Remember this diagram? This here is a transverse wave, right? The particles are vibrating up and down, but they are moving to the right there. Okay? And you should remember what you call those maximum points of displacement. Crest, right? And the negative maximum underneath. Troughs, right? So you have crests and troughs. Okay? So you have crests and troughs. Longitudinal waves, on the other hand, as you will see down here, longitudinal waves, they oscillate or vibrate left to right, right? But they move in the same direction, right? So when they vibrate in the same direction, it's called a longitudinal wave. Where you see the slinky close together is called a compression. Where it's far apart is called a rarefaction. Okay? And later on we will see these things, but what's the distance from a compression to a compression? A wavelength, right? Or rarefaction to a rarefaction. Right? Just like the one from before, crest to crest is a wavelength. Okay? So there are some things that we need to remember about graphical representation of waves. If I gave you a displacement position graph, you cannot read off what? Eric? What you can't read off from a graph like that? Pay attention now. All right? So from a graph like this, you cannot read off any time values. So you can't read off period, nor can't you read off, well, you can't work out frequency. All you could read off is your distance values, like wavelength. So from here to here, that's a wavelength, right? So this entire length here, the length of that is a wavelength, or from crest to crest, that's a wavelength, right? Length of one cycle, right? A cycle looks like this. Okay. So you have the wave profile graph here. Here now you have a displacement time graph, right? What you cannot read off from a graph like this, cannot. All right, what else? Simpler. So you can read out period, right? And you can work out frequency. You cannot read off what? Well, all right. Wavelength, right? Because it's a displacement time graph. So the distance from here to here, you can't read that off because you have time on the axis, right? Right, so just remember those small things, right? So you could read off period here, and you could read off wavelength here, right? I kind of assume you know what is wavelength and thing, right? But let me just go it over here. Period, time taken for one oscillation, right? Amplitude, the maximum displacement from the equilibrium position. Displacement is the vector distance to a wave particle from its equilibrium position. Okay, so for example, actually, watch here. Here to here is the maximum displacement. That's the amplitude, right? If generally you want to get displacement, it'll be like right here to right here, from equilibrium to wherever you want. Okay, so here to here is a displacement, or here to here could be a displacement, and so on. All right. Right, you have your wave parameters here. Frequency, number of oscillations in one cycle. Sorry, number of oscillations per second, right? Let's do a quick favor. You can do it mentally if you want. What is the frequency here? Yeah, mentally. All again? How much? 1/4 hertz, right? Right, so you can do that mentally. 1/4 hertz, right? Right, period is equal to what, Eric? Period, frequency, sorry, is what? One over period, and period from this graph is what? Right, so that's 1/4, so you could work it out, right? 1/4 hertz, sorry, just a quick reminder, right? Good. So you remember that we have no wavelength values here, right? And you have hertz. Just now I'll do phase difference. I just want to talk about wavelength and speed, right? Wavelength is the distance between two successive particles on a wave which are in phase. All right. So once you have 2 points are in phase, you find the distance between them, and that'll be a wavelength. Or an easier definition is the distance or the length of one cycle. Okay. Speed is what? Speed is, I want to show you how they came up with that formula, right? We know speed is distance on time. All right. So if the distance covered is one cycle, that's a wavelength, right? What's the time for one cycle? Period. So V is equal to lambda by 1 on T, correct? Remember, F is 1 on T. So it means that speed is F lambda. That's okay? So that's where it came from, right? So V is equal to F lambda. Right? So hopefully you should know all those things, right? And I'm showing you where it came from, right? Right, before we do phase difference, let's come back here. Tell me the speed of this wave, please. I just added in some values, right? Distance in meters, right? And the period of this wave is also 4 seconds. Find the speed for me. You can do it mentally. Find the speed fast. Yeah, you can message the answer. What you got, Antonio? Ah. Check back. Right, so you should have something like this. I don't know, that's how this link create now working. All right. So let's talk about phase. Oh, sorry, I didn't work this out. V is equal to F lambda, right? V is equal to F lambda. F is 1 on T multiplied by wavelength, which is 4. So that's 1 meter per second, right? 1 on 4, right? The wavelength here, and I gave it period. Okay. All right. So that was the unit. That was the C-sex stuff, right? Let's go now to phase difference. Everybody okay with those? Everybody okay with those? Yeah. Nice, Karina. Amil, Eden. Are you okay with those? Okay, so you want to talk about phase difference now, right? Let's talk about phase first. And I'll show you a simulation to highlight all of this, right? The phase of a particular point in our oscillation is a measure of the fraction of the oscillation that has been completed with respect to the starting point, right? And of course, we do everything in radians, right? For those who don't know what's radians, 180 degrees is pi, 360 degrees is 2 pi radians. So a whole cycle is considered 2 pi. All right. So we're going to use everything in terms of pi, right? Let's talk about phase difference now, right? And I will show you in a simulation just now. The phase difference between two particles in a wave is the fraction of the cycle in radians by which one particle leads or lags the other. right? So you're going to get two waves, one probably here, and the next wave probably start later on looking like something like that, right? We're going to observe what's the phase difference between these two waves, right? Two waves which are exactly at the same point in the path of the wave and which are moving in the same direction are said to be in phase. These particles have a phase difference of 2n pi, where n is a whole number, right? So if two things are in phase, these are the phase difference values. N could be 0, so you can have a phase difference of 0. So this wave and this blue wave perfectly in phase. That's a phase difference of 0. Or the green wave here and the blue wave start right here. Those are in phase, and the phase difference here might be 2 pi. Right? So these are the values that could be the phase difference of something that's perfectly in phase, right? Right? These are the values. 2 pi, then if n is 2, you'll get 4 pi. If n is 3, it's 6 pi. And so on, right? Those are values for in phase. Two particles which have a path difference of 2 pi on 1 will have a phase difference of 2n minus 1 pi. And are said to be exactly out of phase. I'll show you this later on, right? Right? Don't worry with this too much as yet. Let's focus on phase difference for now. All right, so watch this here. Phase difference. This here is the formula for phase difference. The distance between the waves. The distance between the waves divided by the wavelength multiplied by 2 pi. Okay? So let's take a look at these two waves here. Here's what it's saying. The question is saying, just some way work out phase difference, right? P lags Q. Sorry, P leads Q. Q lags P. I would like to know which one there is Q. Which one do you think is Q? And which one do you think is P? Q lags P and P leads Q. Which one is which? While you're in this class, pick up your phone now, right? Put it away. Put it away from now. Yeah. Which one do you all think between the blue and the green? Which is P and which is Q? Online, what you all think? Five, one of the fives of it. Yeah, it are like five singular. It's like we have capital and common. They have plural and singular. So you have a next five, I think. Right, yeah. So from what I'm seeing here, right, from what I'm seeing here, most people saying green is P and blue is Q. Right? So it is saying that P leads Q. So it's looking like the green leading the blue. And then the the green leading the blue and the blue behind the green. Oh, Andy. I didn't get your answer, Andy. He didn't say green is P. I'm waiting on Andy here and Vera. Excuse Vera. Andy, Vera, you're there? Right? Yeah, Andy. Which one do you think is blue? Blue is P or Q? Right? Andy's saying that the blue is Q. Right. So from what we see in here, right, the green looks like the P and the blue looks like the Q. Right? So the green looking like it's in front because it's a displacement graph, right? Right. So how do we get the phase difference? Well, what we need, we taking 2 points here and we finding that distance. The distance between those 2 points is x. And then we taking x and we dividing it by the wavelength. Right? When you multiply that by 2 pi, you'll be able to get the phase difference. All right, so let me just show you an easier one now. Right, kind of hard to kind of work out that value there, how much of the wave it is. Right, watch this one here. Right, I'll show you a little simulation after, right? Right, I'll use blue and green, or like it's green there. I'll use red. Right, so here's what you want to get. We want to get the phase difference between the green and the red, right? Sorry, blue and the red. Sorry, blue and the red, right? So my question to you is this. How much of a wave is that distance there? Or how much later did the red wave start after the blue? How much of a wave is that? Quarter. So watch this here, right? For those who are not too sure, if a wave starts here, here is quarter of a wave. Here, that point is half of a wave. This point, 3/4 of a wave. This point, all of a wave, right? The whole thing. Right? There's a whole wave there. Right? So what you all think? Check it back again. How long after did the red wave start? After the blue? How long after? Karina, check back yours now. Right, correct. How much you think, Shivani, Shoshana? What is that distance there? You are trying to basically figure out this distance here. Right? That's how long it took. That's how long it took before the red wave started. Nice job, Shoshana. Quarter of a wave. So this distance here is lambda and 4. Are you okay with that? How you find phase difference again? X over lambda by 2 pi. So watch this here. X is how much? X is lambda over 4 divided by lambda multiplied by 2 pi. How much is that? You don't need to know lambda. How much? Check it and see that's simplified from now. Lambda and 4 divided by lambda multiplied by 2 pi. Check back again, Shivani. Right? So when you work it out, lambda will cancel and you'll get 2 pi on 4 or a half pi. So the phase difference between the red and the blue is a half pi. Are you okay with that? You okay with that? Online? Are you okay with that? It's not 8 pi, right? Just simplify it out. Based on the note, right? So somebody said 8 pi. Based on the note. No, somebody online said 8 pi, right? If two waves have a phase difference of 8 pi, are they in phase or out of phase? Are they in phase or out of phase? 8 pi. I'm going to show you this. If something in phase, it will be a multiple of 2 pi, right? 8 pi simply means it's happened 4 cycles down the road. All right? You're looking at the concept there of phase difference. It's a little bit hard to see 1/8 and 1/16, right? Right, but you have to be able to identify a quarter, half, and 3/4 thing, right? Are you okay online there? Very probably not there. Harris, Rebecca. You're looking at phase difference. Right, so the phase difference is not pi on 4. The phase difference is pi on 4 over pi by 2 pi, which is pi on 2. Okay, so the phase difference is pi on 2. So if a question tells you that the phase difference is pi on 2, it means it starts a quarter of a way after. Right, do my favor now. Draw two waves that have a phase difference of pi. Draw two waves that have a phase difference of pi. I'll try this now. Draw two waves that have a phase difference of pi, and tell me if you remember what we said about those two waves. Anybody online could draw or take this off? Where in your iPad? Andy, you could draw. Right. Andy, try it now. I'm not sure we're going I'm not sure if it'll work here, but try it and see. Use a different color. Use like anything besides blue. Right? I want you to draw a wave with a phase difference of pi. And see if you remember what we said about a wave like this. Okay? See? Or you draw the next wave alone. You draw two waves or there's one wave there? You have two waves there? Oh, yeah, let me draw it. Yeah, I wasn't seeing the next one. Yeah, Andy, draw it for me now. On the whiteboard right there. Oh, you're not getting it? All right. All right, tell me where to start the wave, right? Tell me where to start the wave. Start it here. Oh, crap. Tell me to start the wave here. Spot 1, spot 2, spot 3, 4, spot 5. Where to start the wave? Andy, what do you think? Anybody? Where do I start the wave? Spot 1, 2, 3, 4, or 5? Good job, Shabani. Anybody else besides Shabani? Rebecca, good job. Nicole here, no? Rika? Where do I start the wave? Spot 1, 2, 3, 4, 5. All right, nice job. So the wave will look something like this. Are you okay with that? Right? I could even draw the wave underneath here, you know. Right? Those two waves, when I find the distance from here to here, that's half a wave. Right? So they have a phase difference of, this is half a wave, right? They have a phase difference of pi. Right, quick question. That blue wave and black wave, they are said to be what? You all did this in CSEC. Right, very good, Shivani. Totally out of phase, right? When we do that in destructive interference. When a crest meets a truck. When a crest meets a truck, right? You have destructive interference. Okay. All right. I just want to show you a simulation here. It will kind of show you how phase differences look, right? I can't really draw beyond pi on 4 and thing. It's kind of hard to draw. Well, for me. All right, so I'll show you this little simulation here. Right, which one is normally work physics lens, right? Got this here, right? The only problem, it's a little too big for you to see everything. All right. So you're seeing two particles there, a black and a red, a black and a blue. What's it now? You laughing at boy? Huh? You what? Oh, as I laugh now. All right, so watch this here. Right? I have a little problem, right? I wouldn't be able to show you the particles all the time, right? But I'm going to let the particles oscillate in phase. Right? So I'm going to play the totally in phase. See that? See how they're looking? Watch their graphs. Identical, right? They kind of overlap each other. Let's change the phase now to what? We learned about pi on 2. Let's see if we can change the phase to pi on 2. Hold on, huh? I don't know how to get it. Maybe I can type it in, boy. Right, that's the best I could do there. Right. So that's 0.5, right? N is 0.5. So it'll be 0.5 pi, which is a half pi. Let's see if we can observe it here. Right? The outer phase by pi. Oh crap. 1 minute. Watch the particles, right? That's what outer phase means by pi on 2. Watch the graph. See that? Y'all see the difference between the blue and the black? By pi on 2? Yeah? Let's change it now to pi. Where did I go? Let me reset it. Let's go to 1, right? I should be able to reach 1. All right. Let's play it. Watch the particles. Watch the particles. Phase difference of 1. Like two other running shuttles, and he way ahead of you. Right? That's a phase difference of 1. Look at the graph. See that? Phase difference of 1. Okay? Online, you'll see the difference in you'll understand phase difference. Are you okay with that? All right, let's try one, but you see, I wanted to really see the particles, huh? Now, let me see if I can redo it. I want to show you how the particles behave. Right, the blue coming down, the black going back up. Anyway, all you can play with that simulation, right? And I really get it. So I can't show you both at the same time. Is there a full screen on this thing? All right, I can't really show you, but you'll understand phase difference online. Online, okay, phase difference. Yeah, right. So I want a small prediction. I want to put a phase difference at 2 pi. What will you see? I'm going to put a phase difference of 2 pi. What will you see, Antonio? What you will see? Huh? How will the particles behave? See if we can predict how the particles will behave. If it's a phase difference of 2 pi, just the particles. And then Sean will tell us what the graph will look like. Huh? And now. How will the particles look? They'll move the same. How the graph will look? And how your next one will look? How much further away do you think it will start? All right, let me see. See, the waves move together because they're in phase. The particles move together because they're in phase, and you're not going to see anything here, right? Because technically the graphs will overlap, right? All that might happen that you might see. You see the black and the blue right there, but the blue might start. Anyway, you basically see that, right? At the end of the day, you will see the same thing because they are in phase. If I carry to 4 pi, same thing will happen. 6 pi, same thing will happen. Okay. All right, nice. So that's our intro into, well, that's our explanation of phase difference. You can calculate it, right? Make sure you can see 1/8 of a wave, 1/4 of a wave, and all the multiples of 1/8, right? Make sure you can see those. Right? There's a nice simulation to play around with, right? It's from they have a few others with physics lens. Right? They have a few others you can look at. Right, let's go back to the notes. Let's go back to the notes. One little thing to finish up. Right, today's more notes than anything else, huh? I don't think I'll rush into stationary waves because that's a whole section of questions, right? Let us continue. We talked about wavelength, we talked about speed, we talked about phase difference. A wavefront is a line or surface in the part of a wave in which all the particles are in phase. So sometimes you might Sometimes you might see a wavefront just like that. Right? You could draw a straight line. A ray is a line perpendicular to the wavefront, so you draw a ray like that. Right? So sometimes instead of the wavefronts or showing the whole wave train, you just draw a ray. Right? Oh, something new here. This is a new quantity. It's called the intensity, right? So if I ask you to find the intensity of a wave, the intensity of a wave, it basically is power per unit area, right? So the rate of flow of energy per unit area perpendicular to the direction of travel of the wave, okay? So this is the intensity of a wave is measured in watts per meter squared, right? So intensity is power over area or energy over time by area, right? That's a new quantity called intensity. So if I ask you to find intensity of a wave, intensity is power over area. Right? We will use it more when we do the air. When we do the air and decibels and those things, we'll use this a little bit more. All right, note that these are the units. Something very important is that the intensity of a wave is proportional to the amplitude squared, right? For all the music people, if you want something loud, what you do? And just increase the intensity. If you have a sound wave and you want to increase the loudness, what you do is increase the intensity, right? So you're increasing the amount of waves coming in. Right? And you should remember that for a sound wave, loudness has to do with amplitude. So if you increase the amplitude, you're going to increase the intensity because intensity is proportional to the amplitude squared. Okay? Right. So we're going to talk about something called polarization, right? Anybody knows where they use polarization? In the glasses, right? And what is trying to do? What do polarized lens try to do? Right. So polarized lens tries to reduce the intensity of the light coming in, right? So it's trying to reduce the intensity of the light coming in, right? So the way they reduce the intensity is by polarization, by decreasing the amplitude of the wave coming in. All right, so I want to show you what is polarization, right? Real easy. There's a simulation, but there's nothing easier than this. Put a diagram there, right? If you have a transverse wave, right? The transverse wave, it vibrates perpendicular, right? So you have EM and EM fields and electromagnetic fields and things vibrating, right? If you look there, you have waves, a red wave vibrating perpendicular to a blue wave, right? If you had a plane polarizer, right? So you had a polarizer, this here is a polarizer, and it's vertical. That vertical slit or that vertical poloid, it will only allow the vertical part of the wave to pass through. The horizontal part of the wave will become polarized, right? Right? So if you want to polarize this vertically oscillating wave, then take the polarizer and put it horizontal. Now nothing could pass through. That's what you have now. Right? So what we have there is a fully polarized wave. Right? Initially it vibrating vertical and horizontal. Then we put the polarizer, it vibrating vertical alone. Then we adjust the polarizer, nothing comes out. So we just fully polarize a wave. That's okay? So let's take a little read of what is polarization, right? So transverse waves whose places of oscillations vary randomly with time are said to be unpolarized. Polarization is the process of restricting the oscillations of a transverse wave so that oscillations take place in one plane only. A transverse wave which have oscillations in one plane are said to be plane polarized, right? So here we plane polarize a wave, right? I don't know what you're laughing at, so. Right, so we just plane polarize a wave. But here's the problem, Antonio. Longitudinal waves such as sound cannot be polarized, and therefore polarization is a phenomenon which may be used to distinguish between transverse and longitudinal. What are you laughing at, so? Right? Here's an example of polarizing transverse waves, right? Right, the free end of a rope is moved to and fro in all directions to produce a transverse wave, where you have planes, waves which are produced by the oscillations in the go take a 2 minutes now. Waves which are produced by oscillations in the vertical planes only are able to merge from the slit in the polarizer, right? You all seen that there? Sean, you laughing too? Right, so the red waves cannot pass through, right? Only the blue. If the analyzer A is rotated 90 degrees, then no waves will come out. And the slits are said to be crossed. Right? I'm missing a little thing there. You misspelled rope twice. Huh? I misspelled what? It's rope boy. It's rope boy looking like. It's a rope boy talking about. Anyway, so I'm missing a diagram, right? I want to get back that diagram. Right, but basically here's what it's saying. As A is slowly rotated, the intensity decreases and falls to 0, right? So it's a polarizer and they rotate in the polarizer and they were able to drop the intensity to 0, right? Lost that diagram. I had to see if I could get that back there. All right, you'll understand the concept of polarization, Chelsea, Trishana, Zaria. You're okay with the concept of polarization? All right. Right, so I'm missing a diagram. I have to find that back. Here's an example of where we take the sun from the light from the sun and we polarize it. Right? So the polarized class we'll have a few. It'll be 0, you know, if you have 0 coming in, right? So there's just a few sets. Right? So what they're showing you here is that you have a horizontal plane polarizer. So every other angle except the horizontal angle is polarized. All right, let's see what it says here, right? So what are the uses? Because caused by light reflected on a smooth surface can be reduced by polarizing materials, which since reflected light is partially polarized. For example, light reflected from the sea is partially horizontally polarized, and in polarized lenses, in some glasses are vertically polarized, then most of the reflected light is absorbed by the sunglasses, right? So they're showing you that here. You know what they're laughing at? I spelled somebody words wrong, that's what they're laughing at. All right, anyway. Right, so yeah, so if you look here, you have this unpolarized light becoming polarized. Okay, the glasses emit only vertical polarized light. So that's all that coming through for you. All right. So the glare overall is reduced. And the way we reduce it is by reducing the intensity of the light coming through. Okay. Right. Electromagnetic radiation from radio, television, radar aerials are plain polarized. If a radio wave is transmitted from a vertical area, then the wave from it will be vertically polarized, and receiving aerial must be positioned vertically, right? So if you polarize something and it's vertically polarized, then the aerial must be positioned vertically. Otherwise, you wouldn't be able to read it. All right. Variation in landscapes mean that the aerial may always be positioned vertically with respect to the ground. All right. Last thing, the superposition principle. Right. You kind of did this in Form 5 already. And make sure I spell nothing wrong here, because I'll laugh again. All right. The total displacement at a point where waves cross is equal to the vector sum of the individual displacement due to the wave at that point. So for example, if I gave it two waves like this and I asked for find the superposition, you're basically taking the vector sum of waves that are in phase, add in here and here, add in here and here, add in here and here, and you will get a superimposed wave. All right, remember this? Constructive and destructive interference. Yeah, destructive is the opposite. Okay, here we have an example. Right, here we have an example. Watch this here. When you have two waves that are in phase, you're seeing that the blue and the green in phase, right? And they superimpose on each other, you'll end up with this large wave here. If the amplitude here is A and here's A, then the amplitude here is how much? 2A. The amplitude there, 2A. And if they are perfectly out of phase, like here, crest meter trough, when you add up that, you'll get 0. And you'll get this destructive wave. Okay? So you have constructive interference, destructive interference, which are two examples of superposition. All right? And more than likely, anybody could guess, I know I didn't show you, but anybody could guess how stationary waves are formed? Since I just showed you superposition. Most likely they form from some form of superposition, right? All right, watch this one here. I'm not sure if you're seeing this. Right, you have two waves there, dotted wave, broken line wave. And the resultant is dark wave. You're seeing that? So here's how they got the dark wave, right? I'm just picking a few points. If you were to take this displacement here and add it to this displacement there, when you add it, you will get this value here. You're seeing that? You just add in points that in phase, right? If I were to add these 2 points here, put it dotted and broken, we'll get this point here. If I were to add this point here and this point here, we'll get this point here. You'll see that? So if I were to add the displacement here and displacement here, you'll get 0. So that's the reason why it's down there. That's okay? Right? Normally I'll give you one to do, but let's see if we can find this one in the simulation. Right? I don't remember the simulation. Give me 1 minute, sir. I don't remember this one. Right, yes, GeoGebra. Last thing I'm done, right, Talia? Today I learn go early, right? But the cast stop line. Huh? All right, last one. Right. So let's take a look at the simulation quickly. Both waves have the same amplitude, right? You're seeing that? Same amplitude, same wavelength. Let us, why are they showing us already? As they move, the pink line showing you their superposition. Right? Let's pause it. You're seeing that? If you would add up the points there, you'll end up with the purple line. Let's play it and pause it right there. Watch that there. You're seeing that they kind of almost out of phase, right? If I were to get them perfectly out of phase, that purple, what would happen to that purple curve? It'll be a flat line, right? Let me see if I can pause it for $5 now. Hold on, try. If you get a straight line, you're getting $5. Now, let me come on, try too. Yeah. I'm on China for $5. Well, I guess top it all again, $5. We lost, I'll take 10. Huh? 3 tries. All right, so basically that pink wave is an algebraic sum of the red wave and the blue wave. Yeah. All the way on again. I'm gonna 3 chances. I'm taking anything. Ball again, $5. If all again. Yeah, 3 chances again once. All right, so that's superposition, right? What we're gonna do next? Well, not today. We're gonna do stationary waves, right? Come on, try it fast now. I'm gonna take off this. Yeah, you gotta stop it at. Yeah, stop it at a straight line, right? Yeah, almost. Yeah, $5 man. I can't try it now. Ah, that's straight. No. Only $5 man. That's straight. I get better than that. Who wanna try? Come now, last chance. All right, Tolia. So